All right, in Calculus 4.4, the fundamental theorem of calculus. We're going to evaluate a definite integral using the fundamental theorem. We're going to understand the mean value theorem for integrals, find the average value of a function over a closed interval, the second fundamental theorem, and the net change. So there's quite a bit here today. All right, so the two major branches of calculus, that was the differentials calculus and integral calculus at this point. These are the two problems that we might seem unrelated, but they're actually very closely connected. The connection was discovered by Isaac Newton and Gottfried Leibniz and is stated in a theorem that is appropriately called the fundamental theorem of calculus. So it's telling me that if a function is continuous on a closed interval a to b and f is an antiderivative of little f on an interval from a to b, then if I take the integral from a to b of a function, so I'm going to integrate the function first, then it would mean after you integrate, you plug in the b minus when you plug in the a, and that would actually equal the value of this. And that's your fundamental theorem of calculus. So it tells me to evaluate each definite integral. So we first start with taking the antiderivative of each, we integrate it. So remember, that's adding 1 and dividing by the new exponent. Now notice this time where the integral symbol was 2 to 1. After I integrate, I drop the integral symbol. I now switch to a bracket, and I now write the 2 and the 1. Notice I don't put a plus c this time, and the reason I don't is because I'm going to plug in the 2 for all the x's and then minus when I plug in the 1's. Well, if I had a c there, I would get c, and then it would be minus c, and that would just go away. If you don't understand what I'm saying about the c's just going away, see me later, and I will actually show you on the whiteboard how that works. So at this point, we take the value 2 in for each x, and then minus, you plug in the value 1 for each x, and then you just find what that equals. All right, to integrate this one, that was square root of x, so I'd want to rewrite it first as x to the 1/2. 3 was just the coefficient in the front. Add 1 to that, that would be 3/2. Remember, divide by the 3/2. Dividing by 3/2, same thing as multiplying by 2/3. So 2/3 times 3 would actually end up being 2. So we end up with 2x to the 3/2, and then plugging in 4 minus when I plug in 1. So there's 2, x was 4 to the 3/2, minus 2x, which is 1, to the 3/2. Now remember, when it's raised to the 3/2, the denominator is the root, so that means the square root, and then to the third. So the square root of 4 is 2, to the third would be 8, times 2 would be 16. This means the square root of 1, that's 1, to the third, that's still 1, times 2. And then you would have your answer. All right, integrating the secant squared, we're asking ourselves the derivative of what is the secant squared. Hopefully you're thinking that's the tangent. Now I'm going to plug in pi fourth minus when I plug in 0. Now the tangent at pi fourth, that would mean the tangent at 45 degrees. The tangent at 45 degrees is in quadrant 1, and that would be the 1 over 1 with the reference triangle. Then I need the tangent at 0. Now at 0 radians, that would put it on the positive x-axis. The positive x-axis for the tangent, remember, that was the y's over x. So the tangent at 0. So let me draw that picture real quick. So if I'm here at 0 radians, at the point is 1, 0, then that tangent would be the y value 0 divided by the x coordinate of 1. So therefore that would be 0. All right, now you have 1 minus 0, and your answer is 1. So if I have to integrate 1 to 4 for u minus 6 over the square root of u du, you first want to rewrite this. Now remember, this is u to the 1, this is 6, and this is square root of u on bottom, meaning u to the 1/2. So I'm going to take the 1 minus the 1/2 and rewrite that as u to the half. Then I've got negative 6 over that. Again, if the denominator is a monomial, the numerator is just some sort of a polynomial, you want to take each term over that denominator and do a rewrite. So I've done my rewrite. Now I integrate. I add 1 to this. That would be 3/2. And then I would divide by the 3/2, means multiply by 2/3. Add 1 to negative 1/2, and that would become a positive 1/2. And remember to divide by that new exponent. Now in your notes that you have, this is actually a not finished problem. I added this one in at last minute because I know you guys needed to be reminded, again, when the numerator is a polynomial, the denominator is a monomial, please rewrite the bottom underneath each one of the tops. And then that way this becomes a much easier problem to integrate. You would do the same if you were taking the derivative of it. All right, so we're supposed to evaluate the integral from 0 to 2 of the absolute value of 2x minus 1 dx. This is what the graph looks like. This would be a v-graph. We should know the absolute gives us the v-graph. The vertex of it, if you take what's inside equal to 0, that vertex is at x equals 1/2. So I'm looking to integrate from x equals 0 to x equals 2. And again, the vertex was at 1/2. This v-graph was not shifted up or down. So basically, I want the area of this triangle here, and I want to add to it the area of that triangle right there. That would be the easiest way to do this. If Calculus 1 is your terminal math class, I would advise you go ahead and just get the area of each triangle. Now, to get the height of this triangle, you would plug 0 into that equation, which would give you 2. So this is a height of 2, and this length is 1/2. 2 times 1/2 is 1, half of that, so this area right here is 1/2. Now, the length across here is 1.5, or 3/2. How high is it? We'll plug 2 into this function. So this would be a height of 3. This across here was 3/2. 3 times 3/2 is 9/2. Half of that, this area would be 9/4. Add those two answers together, and you have your answer. Now, if you're not going to use the geometry method to do this, then we're going to have to understand, if you're going to Cal 2, you should be able to split this equation. Now, this side of the line is the line that has the positive slope. So notice we keep that as the 2x minus 1. But it'll have to be integrated from 1/2 to 2. So I'm going to integrate the 2x minus 1 from x equals 1/2 to 2. Then I would add to that the integral from 0 to 1/2, and I have to take the opposite of that equation, which is negative. So that means the opposite. So it'll be a negative 2x and then a plus 1. So that's how you would have to do that. So again, I'd be integrating from 0 to 1/2, the opposite of this equation, negative 2x plus 1. Add to it the integral from 1/2 to 2 of 2x minus 1. So once you integrate, remember, plug in the top numbers minus the bottom numbers, and then that would be your answer. So again, you have the option of doing this with geometry formulas, or you can do it with the integration formulas. Doesn't matter to me what you do, but if you are going to Cal 2, please practice with the integration formulas here. All right, so now we want to find the area of the region bounded by the graph of this parabola, the x-axis, the vertical lines x equals 0 and 2. So we have a parabola. I don't know where the vertex is. It doesn't tell me. It's not in vertex form. So remember, the vertex would be at the opposite of b, so that's 3 over 2 times a, so at 3/4. Plug in the 3/4 for each x, 7/8 is the y, and we do know the parabola opens up. Now this was important because that tells me that my parabola never crossed the x-axis here. So it's always above the x-axis. I want the area between that graph, the line x equals 0 is here on the left, the line x equals 2 is on the right, and the x-axis is down here. So I want all of that area. So to get that area, I need to integrate from 0 to 2 of the function, dx. Add 1 to the exponents, divide. Add 1 to the exponent, divide. Add 1 to your exponent, divide. Now remember to plug in the top number of 2 minus plug in the bottom number of 0. And that would actually give you my area under that curve between the curve and the x-axis from x equals 0 to 2. So the mean value theorem, this is telling me the area of a region under a curve is greater than the area of an inscribed rectangle and is less than the area of a circumscribed rectangle. The mean value theorem for integrals states that somewhere in between there, the inscribed and circumscribed rectangles, there exists a rectangle whose area is precisely equal to the area of the region under the curve. So that's all it's telling me. There's some value c between a and b such that the area of this rectangle here would equal the area under the curve. That's all that's telling me. See, now let's think about this for a second. F of c, that would be the height of this rectangle. B minus a, that's the width of that rectangle. And it's telling me that that right there equals the area under the curve. Well, the area under the curve is written as a to b of f of x dx. So when we're looking for that mean value theorem, again, remember there was some value c in the interval from a to b, such that's the height of your rectangle times the width of that rectangle equal the area under the curve. So that would also lead into what we call for an average value. See, if I want to know the average of the y values along the curve, well, if I was to solve this for f of c right here, I would divide both sides by the b minus a. That's where this formula right here is coming from. So that's how we get the average value. That means the average of all the y values of a function on the interval from a to b. So it tells me, let's go to this one. Find the average value of f of x equals 3x squared minus 2x on the interval from 1 to 4. So the average value means I want to find the average of all the y values. So I need 1 over b minus a. Well, the interval went from 1 to 4. So there's a and b. So therefore, this right here will become 1/3. And then I'm going to integrate from a to b. That means from 1 to 4 of the function itself. Remember, add 1 to your exponents, divide by the new number. Now, I remember I needed 1/3 of whatever I get after I plug in 4 minus when I plug in the 1s. So again, I'm plugging in 4, so 4 cubed minus 16. Then it's a minus, plug in 1. So plugging in 1 would be 1 minus 1. Well, that's 0. So I need 64 minus 16 and then 1/3 of that. And that would be the average of all those y values along this curve. It also happens to give me where the rectangle would be located. That area of that rectangle equals the area under the curve as well. So I need to evaluate this function. So I notice here I'm supposed to evaluate it at x is 0, then pi 6, pi 4. In other words, like I'm supposed to do the same problem with x. There is a 0. The x is a pi 6, a pi 4th, a pi 3rd. So it might be better just to integrate it first and then go through and plug in all these values for the x's. So we go ahead and just do our integrating. The derivative of the sine is the cosine, so that's where I got sine of t. Plugging in x minus plug in 0. So we plug in x, that'd be sine of x. Plug in the 0, the sine at 0 radians. So the sine at 0 radians means at 0 degrees. The sine, remember, was that y value of 0. So the sine of 0 is 0. So therefore, that gives me just the sine of x. So now I'm supposed to evaluate this at every single one of these answers. So that meant I needed the sine at 0. Well, the sine at 0 happens to be 0. Then I need the sine at pi 6. That means I want the sine at 30 degrees. So if you remember your 30-60 right triangle, so you need the sine of 30 degrees, because that's what pi 6 is equal to. So the sine of 30 degrees would be 1 over 2. So that's where they got the answer there of 1/2. The next one wants the sine at pi 4. So that would be the sine at 45 degrees, which was the 1 over radical 2. And you can actually leave square roots in the denominator in here. The sine at pi 3rd, that means the sine at 60 degrees. So 60 degrees, that would be up top. The sine is radical 3 over 2. And then we needed the sine at pi 1/2. That's the sine up top at 90 degrees on the unit circle. So the sine up here on the unit circle would be 1. So therefore, that was a 1 for that final answer. This is telling me to take the derivative of the integral of this function. So first, if I took the integral of this function, I add 1 to its exponent, divide by the new exponent. The 2's cancel. Supposed to plug in the x minus I plug in the 0, so I did. Now we take the derivative of the function, and I'm going to get 2x. All right, so again, I'm supposed to integrate. So the derivative of what is the cosine? That would be the derivative of the sine of t. Plug in x minus plug in 3/10. Now this says take the derivative of this function. See, the derivative of the sine is cosine. The derivative of that, that's a number, guys. This is a value, like just plain old 5 or 6 or 1/2, whatever it is. Its derivative would be 0. So therefore, the derivative of the sine there was cosine of x. I hope you're kind of maybe noticing a pattern here. So we're going to go to the next one. I'm going to integrate. Okay, remember, be thinking about this pattern. And let's see if we end up with the same answer. I add 1, divide by the new exponent, add 1, divide by the new exponent of 1, plug in the 5, and then minus plug in the x. Now I'm supposed to take the derivative of this. See, the derivative of this function, 0. The derivative of 10 is 0. I need the derivative of each of these now. Remember, that was a minus, so you would distribute that with each one. So that's why that's a negative x to the third over 3 and then a positive 2x. So that derivative is going to be negative 3x squared. The 3's cancel. That derivative is 2. Notice the answer this time compared to that. So if you had noticed a pattern, 2t was 2x. Cosine t, cosine x. Wait a minute. T squared minus 2, this is negative x squared plus 2. See, if you're asked to find the derivative of the integral, and the variable's on top and the bottom is a constant. See, when you plug in that constant, no matter what this is, the derivative of it will be 0. Again, I'm plugging in the constant, so that derivative would be 0. Now this time, I was plugging in the constant first. These two derivatives is 0. And then it was minus, right, the derivative after I plug in the x's. See, so notice I'm plugging in the x's, and then it's the minus after, okay, because it was minus each of those. So yes, that could be a shortcut. Plug this x in, and the derivative of the x would be 1. Plug the x in, derivative of x, but that x is on bottom. That's the constant, so it would be negative x squared plus 2. The derivative of the x is 1. And there's your rule for it. So if you have the derivative of the integral of a to x, again, that's a constant, that's a number, then it would be equal to your f of x. And I prefer to write this dx right here at the end, so that way I don't forget to take the derivative of what that is. Okay, so like I said, I prefer the dx here. All right, so this would be take the derivative of the integral. So in other words, I'm going to do the reverse of the derivative, and then I'm going to take the derivative. Well, we're just going to use our rule. So I'm going to plug in x, so that's x squared plus 1, square root. The derivative of x would be 1, so that would be finished. Square root of x squared plus 1. Now, if that had been on the bottom and 0 had been on the top, then this would be a negative out front. So again, that's still a number down here. So I'm going to find the derivative of this integral. Plugging in that number, that would just give me a big O 0. So I'm going to plug in the x squared, so it's cosine of x squared, but then the derivative of x squared, so then that would be times a 2x, so there's my answer. Now remember, see, these are the upside down ones, right? So it might be easier for you just to think about flipping those. If I was to flip that, that would be the negative of this, where the pi half's down here, x to the 5th. I just know I'm going to get the opposite of. I'm going to plug the x to the 5th in here for t, the derivative of that t, and then just remember to put those to the front. Now you could integrate and then take the derivative if you prefer. That's up to you. All right, a net change theorem. The definite integral of a rate of change of the derivative gives the total change or net change in the quantity on the interval from a to b. This will tell me the integral of the derivative of capital F. Again, remember, once you integrate, you plug in the top number minus the bottom number, and that just gives me the net change of a function. So a chemical flows into a storage tank at a rate of, now remember, at a rate of would mean like the derivative, it's the slope, at a rate of 180 plus 3t liters per minute, where the time is between 0 and 60. Not sure if this is seconds or minutes. Oh, it's in minutes. Find the amount of the chemical that flows into the tank during the first 20 minutes. So we're going to let C of t be the amount of chemical in the tank at a time t. The derivative represents the rate at which the chemical flows in. So the derivative was the 180 plus 3t. And again, I want to know how much has flowed into it for the first 20 minutes. So therefore, I integrate. That means this is going to be t, 3t squared divided by 2. Plug in 20 minus when you plug in the 0. So therefore, there was 4,200 liters in the tank during the first 20 minutes. So the velocity of a particle moving in a straight line where the position function is given time, then its velocity is the derivative of the position function. Also, if I was to integrate the velocity function, remember that's going to be the position function. So this definite integral represents the net change in position or displacement of a particle. So when calculating a total distance traveled by a particle, you must consider the intervals where the velocity is positive and the velocity is negative. When the velocity is negative, the particle moves to the left, and when the velocity is positive, the particle moves to the right. This is referring just to our objects that move to the right and to the left. So again, a positive velocity would mean to the right, a negative velocity would mean to the left. Typically, we're talking about things being shot off from a roof or being dropped from a roof. The positive velocity is going upward, and our negative velocity would be going downward. So to calculate the total distance traveled, we will have to calculate the absolute value of the velocities. Integrate the absolute value of a velocity. All right, so let's say this is my function here. If I was to integrate from a to this point, that would give me a positive value. If I integrate from here to here, this would be a negative value. Remember, this would be kind of like if I was moving backwards. See, this is moving forward, and then this is the negative value, so it's like I was moving back. Then again, you have a positive value, so you're back to moving forward. See, so the displacement, when we integrate this, guys, you literally are going to, in other words, if I started here, I could end up back here at negative 20 feet. Okay, so that's why the displacement can have a positive or a negative value. But if I want to know the total distance traveled, I'm not going to have any of these be negative values. They need to all be positives. So I would have to do the absolute value of the graph and then go ahead and do my integrating. So for your example, a particle is moving along the line such that its velocity is given by this formula in feet per second. What is the displacement of the particle on the time interval from 1 to 5? So the displacement just means to literally just take the integral from 1 to 5 of your function. So add, so that'd be 4 over t to the 4th over 4. This is a 10t to the 3rd over 3, 29t over 2, 20t, plug in 5 minus plug in 1. All right, so that's your displacement. So the displacement, you literally just integrate from 1 to 5 of your function, plug in the top minus bottom. Okay, if you know the velocity, when you integrate, that's position function. Plug it in when we had 5 seconds, how far were you? Minus when you were at 1 second, how far are you? That gives you the displacement from where you started your initial time. So for example, if this was my little pin and I traveled forward 5 feet, backwards 10, and then forward 3, my displacement means how far am I from the original point. Now, if I talked about the total distance traveled and went forward 10, backward 15, now I've already traveled 25 feet, even though my displacement's negative 5 feet. Okay, so understand the difference in displacement and total distance. So total distance for that same problem, once I look at the graph of this, I notice the graph dips down below right here. So if I want the total distance, distance isn't negative. Remember, displacement can be negative, but not total distance. So I would want to integrate from 1 to 4 and then minus integrating from 4 to 5. So again, I would then have to minus the integral from 4 to 5. So you integrate each piece separately, and then you would get your 2 answers. So that would be my total distance traveled. These were the different theorems that we have had at this point in this chapter. And that ends your 4.4. Y'all, we'll see you tomorrow.